So today we're going to talk about sub-octave steerable filters. But before we really get started, we need to talk about what an octave is and what we mean when we say an octave or sub-octave. So octave refers to the bandwidth of the filters. And when we have bandwidth, remember we're working in frequency space for these filter decompositions, and we have our, just say our first row of filters right here, our first subband at 4 different orientations. This is really a filter ring, this ring right here, broken out into different orientations. And as we go to different subbands, lower and lower in frequency, you can see that this band gets closer and closer to the center of the image, which would be the low pass frequency right here. And when we want to go sub-octave, that means we're going to get smaller frequencies than a single octave. So that means instead of this band right here, we're going to get a smaller band. So let's see an example of a half octave radial mask, which is the same as the band. So we have the original filter decomposition right here for a full octave right here on the top row. We have nothing in these other ones right here, just to fill some blank spaces right there. But you can see that when we go half octave, 2 filters can fit the bandwidth of a single octave, and it's not very easy to see because we have this roll off from the transition region, but it's roughly the case. We have these 2 filters right here could fit that one. These 2 filters right here could fill up this space. These 2 filters right there could fill up that space, and so forth. And as we go down right here, we can kind of see that the general area that the full octave, I should say full octave right here, that the full octave filters take up is the same as the half octave ones. You could just see that the transitions are different because we have more filters packed into the same area. So the benefit of sub-octave filters is that we get a better spatial domain support. That is, the filters are smaller in frequency domain, but they occupy more space in the spatial domain because there's an inverse relationship between frequency space and just the regular space of an image. So let's go through this code right here, and we can see the reconstruction is about the same. It's not quite as good, but we're going to basically do the same thing. So now we're going to talk about this filters per octave thing that I told y'all not to worry about. So we have filters per octave right here, and if we're going to go half octave, we go 2, quarter octave, we go 4. And now notice that the filters per octave is going to increase the number of filters. So as we saw here, for the half octave filter, we have twice as many radial masks. So we're going to basically increase our number of filters by a factor of 2, and it's going to increase the over completeness by a factor of 2, since we're going to have more filters. Actually, I'm not entirely sure about that last part about the over completeness, so don't take my word for it entirely. So come in here, we're on the sub-octave. Alright, so right here, so we have the number of filters is increasing by the number of filters per octave, and then we define the octave bandwidth. So if I have 2 filters per octave, my octave bandwidth is going to be 1/2. 4 filters per octave, my octave bandwidth is going to be 1/4. This just describes the bandwidth of a single radial mask. And when you can see right here, this number right here is going to be the radial values that determine how the octaves are going to be, or how the filters are going to be spaced out. So let's just say that we have a depth of 4, an octave bandwidth of 1, and these are our radial values. But if we want to double our octave, or quote unquote half our octave bandwidth, and get 2 filters per octave, we would get something like this, and we would have more thin radial masks, which is what we've seen. So as we go through here, we're going to get our filters, we're going to crop them for visualization, we're going to build the pyramid in the spatial domain, and then get the reconstructed DFT. So here's our high pass and low pass filter are unchanged. Here's just a visualization of the transition region. Now notice that instead of doing 1, I have made it a little bit more abrupt, put it at 0.75. A smaller value here seems to improve the reconstruction error, so we can play around with that. So here are the filters. Now we have a ton of filters. It's gonna kind of hard to visualize. It takes a second, but you can see it does actually get smaller if you look at the cropped dimensions. It's a little bit difficult to tell because I'm cropping them each time, and we're getting a lot more filters to represent this. So here's the low pass and the high pass images. Here's the magnitudes, and you can see they are a little bit different as we go down the line. And here's the phases. You can see that we get a better representation of local phase as we go throughout this. So here's the image DFT. We get a fairly decent construction. We're using a real pyramid and not a complex pyramid in this case, even though we could go to complex. So here's the reconstruction. You can see we get a pretty good reconstruction error. Even though we do have some error, it's very small, and the image overall looks the same. So that being said, that this is a sub-octave steerable pyramid, and this has an application and something called video motion amplification, which is an interesting concept that we could actually amplify nearly invisible motions that are less than a pixel in width over time and actually bring them out of the noise. So I got some upcoming videos for that, and I'll see you all in the next one.